Google's AI just solved a 50-year-old math problem in 19 seconds. And that's not even the scary part.
Wait, what's scarier than AI solving problems humans couldn't crack for decades? So we're breaking down what Gemini DeepThink actually solved, how it works, and which industries get disrupted first.
By minute 4, you'll know exactly which skills become obsolete and which become priceless. Let's get into it.
Welcome to the AI Daily Podcast. Today's news and a deep dive to help you stay ahead in AI.
Today, we're diving into accelerating mathematical and scientific discovery with Gemini DeepThink.
Stick around to the end for today's headlines. Let's dive right in.
So let's talk about the long game. It's easy to get caught up in the weekly feature releases and the chatbot wars, but the truly profound shift is happening somewhere else. It's this evolution from AI that can win a board game to AI that can win a Nobel Prize, and that's not an exaggeration.
You're talking about the whole Gemini DeepThink initiative from Google DeepMind. My first reaction, honestly, was a bit of skepticism. It sounds like a branding exercise, a strategic response to OpenAI's momentum. Are we sure it's more than just a new marketing wrapper on existing research?
That's the cynical and, frankly, reasonable first take, but I think it misses the decade-long narrative arc. You have to go back. DeepMind was founded in 2010. Their mission from day one was to solve intelligence. For years, the public-facing proof points were games. Remember the shock in March 2016 when AlphaGo beat Lee Sedol? The world saw an AI master a game with more possible moves than atoms in the universe. But inside DeepMind, that wasn't the end goal. It was a stepping stone.
A very expensive stepping stone. Google paid around $500 million for them in 2014, long before AlphaGo was a household name. So the bet was always bigger than games?
Precisely. Games are the perfect laboratory for a specific kind of AI development. They have clear rules, a defined objective, win or lose, and you can run millions of simulations to train the model through reinforcement learning. What Demis Hassabis and his team understood was that the core techniques developed for mastering Go, deep learning combined with a powerful search algorithm, could be generalized. They built a system that could explore a vast, complex possibility space and find optimal solutions. The question was, what other real-world problems look like a vast, complex possibility space?
And the answer was molecular biology, protein folding.
Exactly. The protein folding problem had stumped scientists for 50 years. Predicting how a linear chain of amino acids will fold into a complex 3D shape is an astronomical combinatorial problem. It's a search space that makes the game of Go look like tic-tac-toe. So they pointed their game-playing AI architecture at it. The first version, AlphaFold, showed promise in 2018, but it was AlphaFold 2 in 2020 that was the earthquake. It achieved an accuracy level that was considered revolutionary, solving the problem to a degree that it's now a fundamental tool for biologists.
And that's the connection to the Nobel Prize, right? For the AI protein design work. It feels like we're moving incredibly fast from a theoretical AI concept to something that's winning the highest honors in science.
We are, and that's why DeepThink isn't just marketing. It's Google codifying a strategy that has been their unique advantage all along. While the rest of the world was mesmerized by generative AI for text and images, which is incredibly powerful, don't get me wrong, DeepMind was quietly building a pipeline to turn AI into a fundamental instrument of scientific discovery. The Gemini family of models gives them a more powerful, multimodal cognitive engine. DeepThink is the strategic application of that engine to the hardest problems in science and math. It's their answer to the what's next question, and it's a very different answer than just building a better chatbot.
So it's a statement of intent. They're signaling that the AI arms race isn't just about commercial apps and search engine dominance. It's also about who can solve the grand challenges of humanity.
It's a competitive moat built on scientific legitimacy. They've proven the model, from games to proteins. Now they want to scale it. What other fields can be revolutionized by this approach? That's the billion-dollar question. This isn't just about accelerating science, it's about potentially changing the scientific method itself. Coming up, we'll dig into the specific architectural shifts that allowed them to make the leap from the structured world of a game board to the chaotic, probabilistic universe of biology. Okay, so the critical question Alex raised is how you translate success in a closed system, like a game, into an open-ended scientific problem. The leap from AlphaGo to AlphaFold 2 is genuinely one of the most brilliant feats of AI engineering in the last decade.
Right. I'm still stuck on this. The state space of Go is massive, something like 10 to the power of 170, but it's discrete. You have a grid, you have pieces, you have defined moves. Protein folding is a physical process governed by quantum mechanics and thermodynamics. It's continuous, messy, and involves countless interacting forces. How do you even represent that in a way a model can understand?
You change the representation of the problem. This is the core insight. The AlphaFold 2 team, led by John Jumper, didn't just throw more compute at the old model. They reframed the problem. Instead of predicting the final structure directly, they designed a system to predict the relationships between the amino acid pairs. They treated the protein chain as a spatial graph, where the nodes are the amino acids, and the goal is to predict the edges, the distances and angles between them.
Spatial graph. So they're using attention mechanisms, like in a transformer model, to figure out which parts of the protein chain are likely to be close to each other in the final 3D structure.
Exactly. That's the key. The model uses an attention network to pass messages back and forth between all the amino acid pairs simultaneously. It iteratively refines its own internal representation of the protein structure. It's like it's saying, if residue 5 is close to residue 50 and residue 50 is close to residue 150, then what does that imply about the relationship between residue 5 and 150? It does this over and over, building a consensus about the final fold.
And this is where the massive training data comes in. They trained it on the Protein Data Bank, right? The public database of about 170,000 experimentally determined protein structures.
Yes, but here's another clever part. That's not nearly enough data to learn the fundamental physics from scratch, so they incorporated an evolutionary perspective. They fed the model multiple sequence alignments, basically the same protein from many different species. The parts of the protein that are crucial for its function tend to be conserved across evolution, while other parts can vary. By looking at which amino acid pairs co-evolve, the model gets powerful clues about which ones are likely to be in contact in the 3D structure. It's a brilliant fusion of deep learning and evolutionary biology.
Okay, that makes sense. It's not just a pure math problem, it's constrained by biology. But what about the trade-offs? This has to be computationally insane. We're talking about models with hundreds of millions of parameters trained for weeks on thousands of TPUs. Is this approach even sustainable? Or is it something only a Google or a handful of other players can ever hope to achieve?
That is the central tension. The training for AlphaFold 2 was monumentally expensive. We're talking an estimated tens of millions of dollars in cloud compute time for a single training run. That's the big science aspect of it. However, the inference, using the trained model to predict a new structure, is much, much cheaper and faster. It can predict a structure in minutes or hours, a process that could take a PhD student years in a wet lab, and DeepMind made the model and the source code failable. Most importantly, in July 2022, they released a database of over 200 million predicted structures for virtually every known protein on the planet. They democratized the results of their expensive research.
So the trade-off is you centralize the hyper-expensive model training within a few corporate or national labs and then distribute the knowledge generated. It creates a dependency, doesn't it? The scientific community becomes reliant on the models produced by these tech giants.
It absolutely does. And that's a direct consequence of this new paradigm. It mirrors the shift in physics where you have massive shared instruments like the Large Hadron Collider that no single university could afford. Google DeepMind is essentially saying, we have built the particle accelerator for intelligence. Bring us your hardest problems. They're leveraging Gemini's advanced reasoning and multimodal capabilities to go beyond just structure prediction. The next step is to predict function, interactions, and dynamics.
So is Gemini DeepThink a specific new model, or is it more of a framework? Is it about fine-tuning Gemini on scientific data, or is it a fundamentally new architecture?
It's more of a strategic framework that leverages the Gemini architecture. Think of the base Gemini models, Ultra, Pro, Nano, as the foundational reasoning engines. DeepThink is the initiative to build specialized systems on top of that foundation, integrating the architectural lessons from AlphaFold with Gemini's broader capabilities. For example, a future system could read a scientific paper, text, look at a diagram of a molecule, image, analyze the raw experimental data, numbers, and then generate and test novel hypotheses in a simulation. That's a multimodal task that goes way beyond what AlphaFold alone could do. It's the synthesis of their two biggest research tracks. Stick around. After the break, we'll talk about what this means for the human scientist and which scientific field might be the next to fall like a domino. So we've established the how, the technical and strategic underpinnings of this shift. Now let's get to the most important part, the so what. What are the actionable takeaways here? The biggest one is that the role of the scientist is undergoing a fundamental transformation.
You mean it's going to put scientists out of a job? That feels like the standard dystopian take.
No, I don't think so. Not in the short or medium term, anyway. It's a change in function. For decades, a huge part of scientific work, especially in fields like biology, was laborious data generation and hypothesis testing. Trying to crystallize a protein could take years of painstaking lab work. Now, with a tool like AlphaFold, a biologist can get a highly accurate structure prediction in an afternoon. This doesn't eliminate the scientist, it elevates them. It frees them from the manual labor of finding the needle in the haystack and allows them to focus on asking, what does this needle do? Why is it important? What other needles should we look for?
So the scientist becomes more of a strategist or a creative director for the AI. They are the ones who have to frame the right questions and interpret the results in a meaningful biological context. The AI is a powerful but non-sentient instrument.
Precisely. The new critical skill for a scientist is becoming problem formulation. How do you take a complex, fuzzy scientific mystery and frame it in a way that an AI can solve? It's like being a prompt engineer for discovery. You're guiding the AI's immense search capabilities toward fruitful areas. The human brings the intuition, the domain expertise, and the creative spark to ask the questions that matter. The AI provides the brute force cognitive power to explore the solution space at a scale we never could.
Okay, so if you're a researcher or engineer listening to this, the actionable advice isn't to go build your own AlphaFold. It's to start thinking about your own domain's grand challenges as potential AI problems. What in your field looks like a massive search or prediction task?
That's the key. What's the protein folding problem in your industry? In materials science, it could be discovering novel alloys or high-temperature superconductors by exploring the vast space of possible atomic combinations. Imagine an AI that could predict the properties of a material before it's ever synthesized. In drug discovery, it's about predicting which small molecules will bind to a target protein and have the desired therapeutic effect without causing side effects. In climate science, it could be building more accurate models of hugely complex systems like ocean currents and atmospheric chemistry.
Even pure mathematics, people have talked about using these models to search for proofs of unsolved theorems, like the Riemann hypothesis. The AI could explore mathematical space, identifying promising patterns or novel logical steps that human mathematicians might miss.
And this is where the competitive landscape becomes a net positive for humanity. The race between Google and OpenAI is forcing massive investment into these foundational capabilities. Google's DeepThink is a direct play to their strengths: deep, focused, scientific problem solving. It's a different vector of attack than OpenAI's push towards AGI through general language understanding. This competition is creating a wonderful side effect. It's subsidizing the R&D for tools that could solve some of our biggest challenges.
So what should we be watching for next? What's the signpost that this is really taking hold beyond biology?
Watch for the publications. The first signal will be a major breakthrough in a field outside of biology, say material science or chemistry, that explicitly credits a new large-scale AI model for the discovery. When you see a paper in Nature or Science about a novel catalyst or a room temperature superconductor where the authors state, "Our discovery was guided by predictions from a new deep learning system," that's the next domino. That's when you know the revolution is spreading. The second thing to watch is the creation of new open databases, just like the AlphaFold database. When a materials fold or catalyst fold database is released with millions of AI-predicted structures, that's the sign that the field is being democratized. Ultimately, we are at the very beginning of a new scientific revolution. The first was the empirical revolution, observation and experiment. The second was the theoretical revolution, math and models. The third was the computational revolution, simulation. Now we are entering the fourth, the AI-driven revolution of automated discovery. And the most profound implication is that the rate of scientific progress itself is about to accelerate in ways we can barely even predict. Before we wrap up, let's catch up on this week's infrastructure news. There's been a significant development at OpenAI. They've fired a top safety executive, Ryan Bayermeister, for alleged sexual discrimination. According to the Wall Street Journal, this came after she opposed the introduction of what they called an adult mode for ChatGPT.
Wait, they were planning to add AI erotica features? That seems like a pretty major shift from their current safety-focused approach.
The termination followed a leave of absence, and it's raising questions about OpenAI's internal culture and product direction. This could have major implications for how AI companies handle controversial content decisions.
Especially when safety executives are the ones being removed for opposing such features.
Shifting gears to robotics, NVIDIA's making waves with their new R²D² framework for scaling multimodal robot learning using Isaac Lab. The NVIDIA developer blog details how they're tackling one of the biggest challenges in robotics.
Which is getting enough real-world training data, right?
Exactly. They're using simulation to overcome these limitations, potentially enabling robots to learn complex tasks much faster than traditional methods. This could be a game changer for industrial automation. OpenAI has also been busy on the browser front. They've detailed their new OWL architecture that powers their ChatGPT-based browser, Atlas. According to their blog post, they've completely decoupled Chromium from the main application process.
What's the benefit of that approach?
Much faster performance and better integration with AI features. It's fascinating how they're reimagining what a browser can be when it's built from the ground up with AI in mind.
And speaking of AI companies, we're seeing major upheaval at xAI. TechCrunch reports that several senior engineers, including co-founders, have left amid controversy.
The departures are reportedly linked to concerns about AI safety practices and some controversy surrounding Elon Musk's personal life affecting the company culture.
That's a lot of senior talent walking out the door. It really raises questions about xAI's stability and future direction, especially when they're trying to compete with OpenAI and Anthropic.
That wraps up today's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
Until next time.